Hello, class. Welcome once again to our discussion, the continuation of our topic, work and energy. So, this time we're going to solve some problems that will help us apply what we have learned, the concept that we have discussed in the first video. Okay, so here's the problem. An automobile weighing 4,000 pounds is driven down 5 degrees incline at a speed of 60 miles per hour when the brakes are applied, causing a constant total braking force of 1,500 pounds. Determine the distance traveled by the automobile as it comes to a stop. Okay, so here's the situation, class, on automobile traveling in this in the right direction with the road that is inclined 5 degrees. So it weighs 400 pounds and it's traveling at 60 miles per hour. And when it brakes, you're applying the force to brake this car, to stop this car, 1,500 pounds. So we are asked to find the distance. What will be the distance of the car traveled until it fully stopped? Okay, so first we have to evaluate the change in kinetic energy. And after that, we determine the distance required for the work to equal the kinetic energy change. Right, so here's the scenario, class. So this car has an initial velocity v sub 1 of 60 miles per hour. Okay, so it applies the brake at this point, and then still, of course, it still runs. And then the question is, what will be the what will be this distance x when the star stops? All right, so we have to resolve this forces into this body diagram. Okay, so we have here the right. So we consider this as our vertical and horizontal. So this is our normal. No, this is the normal force acting on this car, and then we have here the weight, the weight of the car or the mass of this car. Okay, the brake in this direction. So of course, the direction of the force applied to the brake should be opposite to the direction of the movement of the car. Okay, so evaluate the change in kinetic energy. So first we need to solve for the velocity in terms of feet per second. So we're given in miles per hour. So we convert this. So we know that 1 mile is equal to 1 mile is equal to 5,280 feet. So we use this conversion. So 5,280 feet per mile. So mile and miles cancels. So mile divided by mile is equal to 1. So this mile here equal to 1. Mile divided by miles 1. And then we have now the unit is in terms of feet per hour. But we need per second result. So we have hour here. So hour at the numerator. We have hour at the denominator. We know that 1 hour, no? 1 hour is equal to 3,600 seconds. So we use that conversion. So we have hour at the numerator, hour at the denominator. So okay, so 1 hour is 3,600 seconds. So hour numerator, hour denominator, so that cancels out. And then we have when you multiply divide by 3,600, we get 88 feet per second. Okay, so now using the formula for the kinetic energy as mentioned in the uh, first video, so we have here the formula that is 1/2 mv squared, or our velocity here is v1, the initial velocity. So we'll be able to solve for the kinetic energy, that is 1/2 mv squared. So 1/2, our mass here is 4,000. Okay, that is 4,000 pounds, because this is the mass, and then to convert it into sorry, we have mass, mass mv squared. So we convert this uh, because we are given the weight. No, the weight is, we have this relationship class that m is equal to weight over the gravitational acceleration. Okay, so we're given the weight. Okay, so you divide that by the gravitational acceleration, so we have the mass. So we have mass, which is equivalent to weight over g. So our weight is 4,000 pounds divided by 32.2 feet per second. All right, and then we have 88. So this is the one that we have converted, sorry, calculated. Okay, this is our v1, then square. So we got here 481,000 feet pounds. So this is our kinetic energy. Okay, and take note that when the car stops, so the velocity here initially is v1, which is 60 miles per hour. So when it stops, so the velocity becomes 0. Okay, and then the kinetic energy at this point here is also equal to 0. So when the car stops, the kinetic energy at this point also equal to 0. Okay, because from the formula, no, why t2 is equal to 0, we have t. So the kinetic energy at this point here is equal to 1/2 mv squared. So our v is v2. Okay, so our v is v2, but v2 is equal to 0 when the car stops. Okay, so when this is 0, so therefore t2 is also equal to 0. Okay, so that's the reason why we have here t2 is equal to 0. Okay, so next is determine the distance required for the work equal the kinetic energy change. So from this illustration, from resolved forces, no, we have this illustration class, the free body diagram. So if this is 5 degrees the inclination, so from with reference to the normal, so the angle between this weight and this normal line is equal to 5 degrees as well. So we have this illustration class. We can form something like this. Okay, so we have, so this is our 400. This is our force, which is 4,000. So this is 4,000. Or I can expand that a little more to make it clear. So let's make it a little bigger. So we have to magnify this part. So magnifying that part, so we have something like this. It will look like this. So this is our 4,000 pounds, the hypotenuse of this, because we form a triangle here. Okay, so this is our F, and this is our, we can consider this is as our F, the component, the horizontal component of this one. Okay, so this is 5 degrees, and so along this horizontal, so if we use sine, so sine of the angle, that is 5 degrees is equal to, from trigonometry we have sine is equal to opposite over hypotenuse, or opposite here is f of x, then multiplied by the force, or this weight here, that is 4,000. Okay, so we can say that the force along the horizontal parallel to this is equal to, this is our fx, so equal to 4,000. So you cross multiply this, 4,000 multiplied by sine of 5 degrees, sine of 5 degrees. Okay, so we have a formula that the work is just the product of the force. In this case, force, so we use the force Fx multiplied by the displacement, the displacement from, meaning this one, this is the displacement x. So the force along this with respect to the weight of the car, so this is multiplied by x, multiplied by x. Okay, so that's why we have from here we have 1000. Okay, so I will erase this one. I'll just show you how these things is calculated. Okay, so the work, so the work from done from 1 to 2, meaning from the position of the car, okay, from 1 to 2, from the time that it brakes, apply the brake, and then to a stop. So we will use this formula. The work is F up along the horizontal multiplied by the displacement, that is x. Okay, so we have the force here going in this direction. So that is 1,500, 1,500 multiplied by the displacement, because the work here is the total work done with this one, and also the this one. This is the fx that we have calculated a while ago. Okay, so this is negative since this is going on the different directions, assuming going to the left negative, and this one is positive. Okay, so this is the one that we have calculated a while ago, that we have for example, this we have a triangle here shown a while ago. So this is our f of x, and this is our 4,000 here, the weight, and this is our 5 degrees, and this is 5 degrees. So you have to take sine, so sine of 5 degrees, so this is equal to f of x, no, sine opposite over hypotenuse, so f of x and divided by 4,000. Okay, then you have cross multiply, so I have 4,000 sine 5x, so our f of x here, so after you cross multiply 4,000, so you have 4,000 multiplied by sine, Okay, so this is our f of x. This is our f of x. This is our f of x. So now we have work. No, the work is the total work or the resultant work is the work done by this force, that is the braking force, and also the force that is due to the weight of the car. Okay, so summation of this, so we have here the resultant work done. Okay, so this is of course the formula is work is just the product of the the force multiplied by the displacement. Okay, so this is multiplication. Okay, so this one we have this force multiplied by x, the displacement. So we have that work going in this direction, and you have work due to the weight of the car going to the right direction. So this is the one that multiplied by its displacement, that is also x. Okay, so we got one, or sorry, negative 11,000 or 1,151 pound multiplied by x. All right. So total, now the total work, sorry, kinetic energy. So when you look at the kinetic energy, so T1 meaning the kinetic energy at the point of the braking, I mean applying the brake. No, we have T1 and then the plus this work. Okay, then equal to T2, meaning the kinetic energy when the car stops. And we know that when the car stops, so the kinetic energy is equal to zero. So substituting, we solved this already in our previous slide. We have solved this already. So this is the result after our solution for this part. And this, we get this one. So substituting this one here, and then since T2 is equal to zero, so now you can solve for x. So by algebra, we can solve for x that is equivalent to 418 feet. Okay, so if you look at this problem class and see the solution of the other solution, then you can see that we got the same result. All right, so I hope you understood the method, no, in solving this problem using the work and energy. Thank you very much and hope to see you again in our next video. Bye.